In the previous video, we trained a convolutional neural network. In this video, we're going to look at what these convolutional filters are actually looking for in a brain MRI image. Stay with me. Hello everyone and welcome to ML Done. So, as you remember, in the previous video, we trained a dumb model and we looked at the output and we saw that, okay, for positive and negative examples, the output of the neural network actually really clearly is different. And that was beautiful. In this video, as you can see, we're going to be visualizing the feature maps of the convolutional filters. In other words, what each filter is looking at. So for each filter, we're going to grab the learn filter, right, which is just a bunch of weights, and we would convolve it across all of the pixels of the entire input image, and we look at the output. Wherever there's a similarity between that particular small convolutional filter and some locality in the actual image, you would see brighter pixels in the feature map, or let's say brighter values in the feature map. And if there's not much similarity, you will see low values. So that's the very basic, the definition of convolution and convolutional filters, because all you're doing is you're doing a dot product, and that's a measure of similarity, right? So, as a reminder, the model that we've trained, if we look at it, we have two sequential components to it, right? One has two convolutional filters, convolutional layers, 10H operation, average pooling, and the second sequential object has a linear and two and three linear layers with some nonlinearity in the middle, right? The question is, given an input image, what each one of these filters are going to be looking at. So you have input channel as 3 because that's the number of input channels in the image we have, because we have channels RGB, remember? And 6 means we're going to have 6 filters. Each of them is going to be a 5 by 5 sort of matrix. You could think about that, like a 5 by 5, basically 25 weights, right? So we're going to grab each one of these 6 filters and each one of these 16 filters, right? And we're going to be convolving each one of them across the a sample input image and look at what the result is. It's going to be interesting, right? So before I continue, I'm going to just define a couple of variables, right? So I'm just going to call a variable number of layers and equal it to 0. You'll see exactly why I'm doing this. And also, I'm going to define a list. Now this is gonna hold the convolutional layers that I have here, right? And you see exactly why I'm doing this. Now the other thing that I'd like to point out here, suppose you'd like to go through the actual layers with the actual learned weights in your convolutional model, right? So it's important to be able to do that, to be able to iterate through different components of a trained PyTorch model, right? The way you do that is by a method within the PyTorch model, which is children. So you literally write PyTorch children. You can also, return the results as a list. This is very important. Why isn't this happening? Sorry, so it's a method, so I'm gonna have to go parentheses, yeah. So you see it's a list of 2 items, right? First one is one sequential object, the other one is another sequential object, and each sequential object has been indexed in its components 0, 1, 2, 3, 4. Already you see that you can access each one of these components as you would do for any other list, and within each item you have indices that would allow you to iterate through them, right? So already we have nice sort of index style format here. So I'm going to call this model children, right? Just put this in a variable. As simple as that. You'll see why I'm doing this. Now, what I'm going to do, I'm going to start a for loop. Let's say for child in model children. So I'm iterating through these children. It means that model children, again, just to have this right in front of you, it's a list, it has 2 items, right? So I'm iterating through these items. It means it's going to become first this sequential object, and then the second iteration is going to become this sequential object. Am I clear? Right? It's very, very straightforward. So nothing different to a typical for loop that you'd have, right? Inside the for loop, I'm going to look for the items that are of sequential nature. So that, I mean, you don't have to do it like this, because obviously all the like both items are of sequential nature. But sometimes when you code up your neural network PyTorch model, sometimes you don't use a sequential sequential command. Sometimes you just literally code up the layers separately, right? That is why you sometimes need to be able to specify these conditions. So this is supposed to also teach you how to, be more selective in how you iterate through a trained PyTorch class or PyTorch model. So you can say if the type of child is equal to a sequential object is a sort of subcomponent of the NN module class, right? So here we have to say NN dot sequential, right? So just the word sequential doesn't mean anything. Now, if what I'm looking at is a sequential object, which this whole thing is, so is this other guy, right? In that case, I'm interested in looking at its children. You see, this is the beauty of object-oriented programming. Not only the entire model has children, which would be like the first sequential object and the second sequential object in this case, but also each child, which is in this case a sequential object, you can call the children method again on top of that to see what is inside that one child, right? So that's the I would say that's the beauty of object-oriented programming. So you can look at each layer inside a child, right? So you can say for layer in child dot children, right? So the children of the child. I hope that the names are not too confusing. Obviously, you can put, select any name you want. So for this child, the children would be this layer, this layer, this layer, this layer, this layer, this layer, right? So this is where I'm gonna iterate through those layers. Now, I want to say, as you're iterating through each layer, if it's a convolutional layer, I'd like to record it. I'd like to put it in my conv layer list, right? And I'm also going to increment the number of layers that I've recorded. In other words, this guy is going to count the convolutional layers in particular. Why just convolutional layers? Because that's what we set out to do from the beginning. We'd like to see what each convolutional filter is looking for. So here we say that for each layer in child.children, again, I forgot that this is a method, so we need parentheses. If the type of of layer is equal to convolutional layer, right? Again, conv2d, which is the guy that is here, it is a sub method of nn.module, right? So this is why you have to say nn, and then you put conv 2d, right? So if the type is that, only if that's the case, first the number of layers, just increment it and record this, right? So record this layer, conv layer, because we're going to only use these convolutional layers to convolve the filters inside of them across a given input image to look at the feature maps, right? So it's a list, so I'm going to append my layer to it. Yes? So that's about it. It should run, and it ran, perfect. If I look at this list, you see we have two convolutional layer operations, right? The first, two convolutional layers. Now, each convolutional layer, this guy has 6 filters, this guy has 16 filters. If you wanna like look at an individual, layer, you can like index it, like just like you would index in any other list. And you said this would be the second component, which has 16 filters. Now, let's look at one given input image, right? Let's just pick one image. I have a simple code here. No need to waste time on this. So from our MRI dataset object, I'm just going to grab the 100th index. I'm going to grab the actual image. Then I'm going to reshape this. So these are the things that we've discussed before. So this is just a way to grab an image. So this is going to be my input image. That has a tumor, by the way. And remember that these convolutional filters have been trained to classify tumor versus healthy, right? Now, next, I'm going to put my image on my GPU. So, first of all, this is a NumPy array, so I turned that into a torch tensor, and then I put it on my device. As you remember, the device is a GPU. We've defined the device and all of these things in the previous video, so I don't want to waste too much time on this. And remember that as you pass your image to your convolutional filters, remember that the convolutional filter expects that the dimensionality of one given image consists of 4 components. The first one is going to be the number of samples in a mini batch. Second component is the number of channels. Third and fourth are going to be the width and the height, or the height and the width. I don't remember, but that doesn't matter. Now, just to show you the dimensionality of this tensor, shape. You see, 3 channels, height, width. So we need to add one more dimension here, which is going to be 1. So that is why I'm going to do this trick. So just unsqueeze, which adds another dimension across the first dimension, right? So this is what we get, right? Now this is where the magic happens, right? So I'm going to define a list results, right? This is going to hold the feature maps, right? So every time you get a convolutional filter and you convolve it across an image, the result is called a feature map. So in this list of results, I'm going to pass my image to my very first convolutional layer, right? So how do I do that? This is again another beauty of PyTorch. So I have all of my convolutional layers in this conv layers, right? We've already seen this. Again, I think, yeah. Let me just get rid of the index so you can see. So we have 2 convolutional layers, PyTorch convolutional layers. So I'm going to grab the first layer, right? The first convolutional component, which has, what was it, 6 filters, was it? Yeah, the first one has 6 filters. How do you pass the image into this component? You literally put your image inside parentheses and that's it. You pass it to it. This chunk over here grabs that image, convolves all 6 filters against this poor one image and produces 6 feature maps, right? So that's what it does. So the results, if I run this, will have those feature maps, but don't rush. Let me continue. Remember that we have another convolutional layer there as well, which has what? 16 filters. The result of that should be 16 feature maps, right? So what I'm gonna do is I'm gonna define another for loop. Again, we can do it much simpler. I just want to show you like if you had many more layers, many more convolutional layers, you could actually iterate through them. Otherwise, obviously here we only have 2 convolutional layers, so I can just add the second convolutional layer on top of this, right? That's easy. I just want to show you how it's done in a bigger scenario. Now, I'm gonna go in the range, And then I'm going to start from 1. Remember that the first element has already been filled with the feature maps of the first layer convolutional component. So len of conv layers. So len of this guy is 2, right? So the first item has already been manually filled, so we start from the first index. I know it's also the last index of it because it only has 2 components, but again, this is the general approach of fixing this issue, right? Or visualizing the feature maps. Now, I'm going to append to my results the feature map of each convolutional layer that I observe through this list, right? Now, the next, if I append, the next one is going to be the second item of this results list, right? Now, all I do is, of my convolutional layers, the ith index, which starts from 1 now. So the next convolutional layer of conv layers list is going to be grabbed. And then, this is the beauty of it, right? This chunk is really nice. This is very interesting. The very last, remember, the very last output of the previous convolutional filter is going to be the input to the next convolutional layer. Did you get it? Like this is very, very interesting. So here, I would like to say whatever is already inside the results, grab the very last one of them, right? So in other words, the first item here is the first feature map or feature maps, which are the outputs of the first convolutional layer, right? Now, if I want to look at the outcome, the feature maps of the next convolutional layer living in the first index, which is this guy, I have to pass to it not just the original image. Remember, the original image has already gone through the first convolutional layer, which had 6 filters. The results of that has jumped out 6 feature maps, which means it's going to have 6 input channels for the next convolutional layer. That is why we pass the very last feature map that we've recorded into our next convolutional layer. The same story applies if you had 1,000 convolutional layers. The idea is that you pass the very last one to the current convolutional layer, right? So you don't pass the actual image, it's the feature maps generated by the previous convolutional layer. That's the main thing, right? Now, if you do that, the results will have all the feature maps. Now, I can also say outputs results. You don't have to. This is just an extra layer of, you know, being lazy maybe. Oh, sorry, I also forgot this, right, for in. Right, perfect. So now we have all the feature maps. Now, if I want to look at the length of this guy, before I print it, you should know how many items this has, right? 2. But this is the interesting. What are the dimensions of each one of those items? So if I want to look at the first item in the list and look at the shape, guess, before I print it, try to guess, well, not guess, well, give the answer. I think you've understood exactly what this should be, right? So 6 outputs, right? 6 output channels. So 6 output channels were we had 6 filters, right? So that is why the output of the first convolutional layer has 6 channels, right? And because we didn't have any padding, the size has shrunk, right? And if I put the same thing here, but this time for the second item, because we had 16 filters, again we have 16 channels here, and this height and width have again shrunk further, right? Now, this is a very simple code over here. Now, for, let's say, I'm just going to create a for loop that would go through these outputs and visualize them. So this chunk is literally just visualization. I mean, I might as well just copy and paste my code here, because I mean, it's very easy and straightforward. No point in wasting time on this. Now, outputs, the length of it has 2 items for each layer, right? We create a figure. We look at the output number of channels. So this over here becomes, for example, this whole tensor, right? But we are squeezing it because we don't need this first dimension anymore, right? So we only added it so that we could pass our image in through our PyTorch convolutional layers. So we don't need that anymore. Actually, Matplotlib doesn't like that additional dimension. That's why we are squeezing it now. So this layer viz guy is going to be the entire tensor, for example, but without the first dimension. So it will only have 3 dimensions, right? So just printing a statement that, okay, which layer am I printing now, and then through that tensor, for example, 16 by 120 by 120, what I'm doing is I'm going to create multiple subplots. So for example, here I'm going to need 16 subplots to plot 16 feature maps. For the first item, I'm going to need six subplots, right? So because I just want to make sure that I'll have enough subplots to print everything. So that is why I just put 2 by 8 here. So 16 is enough. So that is why I just picked those 2. And then this I just keeps incrementing until I plot all the feature maps in my first layer, first item of the outputs list, and then the second item. And if I want to show my actual tensor, remember that I'm detaching it. Again, we've discussed this in our previous videos. What does detach mean? So we detach this from the computational graph. We don't need that connection anymore. We put it on our CPU, and then we turn it into NumPy, and then Matplotlib easily would plot it off. And then this is just to get rid of the axes labels and ticks. And then we show, and then we can close the plot. We don't even need to. I don't think we need to close it anyway. But anyway, that doesn't matter. Now, if I print this, look at this beauty. So the print statement, right? Remember, I said in the first, let me also print this here, just so you remember what we have. So you are looking at this, like the first layer, 1, 2, 3, 4, 5, 6 feature maps, and the second convolutional, like conv2d PyTorch component had 16, right? So we have 16 feature maps. And just as a reminder, remember, in our model, we are looking at the actual result of 6 convolutional filters being convolved against our image, which has resulted into 6 feature maps. And then the result of 16 convolutional filters being convolved on not the original image, but the feature maps that we've gotten from here. Okay? So that's the idea. Here we've got all of the feature maps, and you can see that there are some very nice patterns. Some of them don't look too interesting, but some look like really, really interesting. Especially like these two seem to be sort of inverse of one another. So the brighter the color, it means that that particular filter, when it was convolving against our image, had similarity across the board here. So these dark parts means that this filter was not interested in that part of the input image, but it was more interested in every pixel that is bright here. Here, this filter, whatever it is, it was looking at the opposite of this filter, right? So try to be able to interpret these results. It was looking for a pattern like this, like imagine, so you've grabbed the filter and sort of convolved in 5 by 5 localities and have slided the filter down the road. It just so happened that these parts of the image had certain patterns that were similar to the learned filter that has resulted into this feature map. And then the second Conv2D PyTorch layer that had 16 filters, each filter was basically ran across, you see, like all of these guys together. And that is why you've got like 16 filters here. Like the output was 16. Remember, the input to the second Conv2D had 6 channels, right? So this is the input data for the second Conv2D. So each filter will be filtered against 1, 2, 3, 4, 5, 6 feature maps. The result would be averaged out or maybe summed, somehow aggregated, right? And then that becomes the result, the first feature map. The second filter of those 16 filters will be convolved against this guy, this guy, this guy, this guy, this guy, this guy. All of them would be aggregated. That will be the second feature map, right? And that's how you get very, very interesting features. And this is what the results, these are the feature maps and patterns, let's say, that all of our filters are looking for in the data. And this is, remember, again, this is the network that was trained so well that was able to classify the tumor and healthy brain MRI images very, very beautifully. And as you can see in our confusion matrix, the accuracy is 100%. There we go. I hope that this was useful for you. Now we understand what our trained convolutional network is looking for in the input data. Hopefully in the next video we're going to be looking at the concept of overfitting and actually see what happens when our model overfits to the data. That is where we will be looking at something called the training error, and the other one is going to be the generalization error. So see you in the next one.